Okay, so what we're going to do now is look at fitting some carbon spectra. Now, with the Varmus file carbon core levels for fitting, again, you will have 4 data sets in this. Data from HOPG, which we've seen a few times in the presentations. An oxidized graphitic carbon called O2 with the highest proportion of carboxylate type functions, and we can see the difference in the spectra here. Adventitious carbon from a titanium material, and a graphitic oxide or graphene oxide type material as well. Now you can play along with those. The demonstrators have the sort of fits to this data, which fit the known chemistry and also the known carbon-oxygen ratios for the whole data set, etc. But we're only looking at the carbon 1s here. But what we're going to do, just to get a feel for fitting the data, is we're going to look at probably the most challenging in my opinion, and that's the pure HOPG. So if we look at this data set, first of all we need to make a region. So we click on the quantify dialog box. Again, I'll move this over here, and we'll say create. It automatically puts on our Shirley background, and you can see it's come in with average width of 3, which I've used previously on this. The average width determines the number of data bins either side of this blue line. If I actually show you what that means in terms of our data, if I go to our display parameters dialog and go to our colors, then if we tick mark region average width, we can see it puts on these dotted lines, which means it's going to average the data from this central data bin to a few number of data bins that we determine either side of the average width. So again, if I change that to 1, we can see it narrows. If I change that to 5, it increases. Of course, these data bins must be within the spectra. If I change this to 20, then we can see it goes off either side of the spectrum. So somewhere in the region of 3 to 5 is generally okay. If you don't have very noisy data, you can go larger as well. But let's just set this to 4 or thereabouts. Okay. Oops. I'll just turn that back off just for clarity, and we have our spectra. Okay, so let's start creating some line shapes. So to do that, we go to our components dialog and click on create, and this automatically puts in one of our default line shapes. So this is the LA 1.53,243 peak, which is my default in HarwellXPS, and one which I said is pretty good as a general Gaussian, Lorentzian or Voigt approximation to a Voigt type functions. So the LA line shape has 2 parameters that we can see here. So we've got LA, as I say, 1.53,243. The LA line shape is actually 3 parameters, but if we exclude the second parameter after this 1.53, then it takes the second number to be identical to this. So for example, if I was to change this number to 1,100, we can see we have this much more Voigt or Lorentzian type function where the tails come out. If I explicitly put in that other number 1 and hit return, again the data hasn't really changed. If I change this second component to number 2, for example, you can see if I colour that in, it's pulled this right hand side of the peak inward. So what we want to do is generate a peak which is suitable for this sort of asymmetric shape. So let's just delete that and start again. So we want something with some asymmetry. So we will use the 3 parameters, and let's start with, if we know 1, 1 and the third number It's 243 at the moment. I should point out this number was the first two digits control how much the wings, if you like, of the peak go out to the higher bind energy side or the lower bind energy side. The third number, which can be a value between 0 and around about 500 from memory, it basically is an amount of Gaussian which is used to convolute a Lorentzian peak form. And you can play around with that number and see how much or how it changes the peak. So let's just go for 1,1 to start with, and we'll go for 200. And we get this Voigt-like or Lorentzian type function. I'll change this component index. -1 means it's ignored. If I change that to 0, it'll change the colour. So again, I change that to 5, it'll be the 5th colour in the HarwellXPS palette. Let's just use that so we can see how the peak is changing. So I want something which will give me more asymmetry to this left hand side. So let's change that to something like, let's try 0.7, and we can see that the peak has come out to the higher bind energy side, and if I manipulate this peak, we can see that that somewhat fits our data. So we're in a pretty good position there already. So, of course, if we fit that, it fits pretty well to that point. But we do have, if I zoom in on this section, you can see our tail goes out over our data. And we still got our satellite functions there to fit as well. What you'll find with carbon data is sometimes, if I zoom in down here, turn off our normalization, the data extends above the peak, or above the peak extends above the raw data. So when you're on components, you can drag the bottom of the data and just drag it down slightly to change your endpoint. And you can do that on this sort of screen as well, and you can fit the data there. Okay, so what we want to do now is look at this sort of pi to pi star area. So if I create a peak, CASA is pretty good to finding where peaks need to go. It uses a simple algorithm for when you've got a peak in place, it looks for the next sort of most intense area. And I'll just copy that peak again and paste that in, and if I click on that second peak and hold down the control key, then I can just, if I hold down the, let's change the number, and there we go, hold down the control key, I can just move that peak. And if I say fit, then the fit goes a little bit crazy. So I delete that and zoom in on this area down here. We can see, although it's fitting the data pretty well, it's not fitting it as we would expect. So let's just put another peak in there for the moment. Let's just call that number 4. Oops. And fit that. So what this has now done, if I zoom in on this further area, is it's fitted the data at satellite sort of peaks, and in roughly the positions that we expected them to be based on our previous knowledge, around about 7 to 10, in the region of 6 to 10 EV away from the main peak. But what you'll notice is we've had to put in, there's a peak here at 286.9, that's constrained at the moment, so let's just release that constraint and fit that. And what you find is to get a good fit to HOPG, you need to put in this peak shape here. Now this is not a chemical state. Because of the intricacies of this HOPG line shape, and there's an area here which is related to defects in the material and the natural asymmetry of the peak. And without doing fancy tricks with the background, or creating different types of backgrounds, we need to account for that asymmetry. So this peak here is something which I can freely remove, but you can see we lose a lot of the definition on our other peaks. If I just recall what we had, putting this peak in, we're quite stable with a peak model. Now, if we look at the residual of this, so we just click on residual on off, we don't have the best fit. The residual standard deviation should be for pulse counted data, which is common in a lot of modern spectrometers, should ideally be below 1. We always think of a good standard deviation to be 1, but really it should be around about 0.9 or so on such data. We can manipulate the backgrounds a little bit and just play around with the data, and we can see just by doing that the residual improves somewhat. Again, we can play around with our line shape. Maybe instead of 0.7 it should be a little bit more asymmetric at 0.65, and we can refit, but we can now see it goes over our data points, so we can just click recall from list and it'll come back. We can of course tie all this data, all these together, so if we think that this peak is always going to be at this point, we can constrain it by saying it is just going to position constraint and typing in A, which means it's always going to be 2.2 electron volts away from A. If we think the full width half maximum isn't going to change, again we can go to full width half maximum constraint and type A, and we can do, if we think the area doesn't change, we could do the same there as well. So now we have a constrained model. If we think we could then, if we wanted, obviously call these all 0, so all becomes one line shape, and we could obviously name this as SP2. If we do that, hit equals in front of our first, in front of the name, then everything with the same component index, which is why I've set all these to 0, will be, say yes, will all come equal to that. And again, we could obviously link all these together or lock them. Lock is a better terminology. Use the term lock in position constraints, and everything with the same component index will suddenly become A plus something. And there we are. There's the values that we roughly said before, about 6.5 EV and about 10 electron volts. So I've used this line shape for this particular example, and it seems to be pretty good. You will get subtle changes on this line, on this residual standard deviation. Although this is a larger number, in all honesty, this works pretty well with very minimal difference in terms of applying just small tweaks to try and improve this slightly. Have very negligible differences on these relative percentages, or therefore the total percentage of an sp2 type carbon within the material. So to give you an example of, this is just something we've just derived, so to give you an example of a different line shape or different parameters which you might use, I'm just going to take a copy of that data and I'll take it with the fitting in, so I won't take process copy only, and say yes, and we've got this exact same data here. Now I've got another peak model which I'm just going to say, so I'm going to go paste replace, so I've got it in memory, and these are color coded differently just so you can see the peaks, but again you can see subtle differences in the numbers. Although these are the same, I've used 0.65, 0.9 and 300 in this case. If I fit that data, I get a residual standard deviation of 4.14, 4.3, 4.14. If I overlay these two data sets, there's very negligible. You can see the residuals basically are the same, and all with subtle differences. Yes, if I lock all these together, you can use the lock all function if we have different component indexes, and again lock all for the photo width half maximum, and maybe the area as well. Again, we can see our positioning in this case was 6.5 and 10.3, 6.6, 10.2, again within our experimental error. And of course we could, if we wanted, reset these numbers by typing the word reset, and then go into the component index, type set equals 0 to set them all to 0. And again, these two spectra, although they have different line shapes, or slightly different line shapes and slightly different positions, are to all intents and purposes identical. So that gives you an idea of how to play around with the LA line shape. You may find you want to experiment with the LF line shape, which basically dampens the tail by adding a fourth parameter to this data. To have a chat with the demonstrators about that, or equally, if you wish, you can just go to Google, and if you Google HarwellXPS LA line shape, you will find this document, Lorentzian asymmetric line shapes. There's the URL, HarwellXPS.com/help_manual_updates/LA_lineshape.pdf. Equally, if you go to the HarwellXPS YouTube channel, you can type in LA into the search field and you can see discussions on Voigt and GL line shapes, and this is what I was mentioning earlier in terms of the Voigt functions, the LA functions being less susceptible to noise in your data. More discussions on the LA line shape, and this time fitting sulfur peaks in tungsten disulfide, and lots of other peak models and data which will discuss the use of different line shapes. This is a very interesting one as well. This uses the Doniach line shape for graphitic carbon. You may want to look at that and see how you can apply that to the to the data we have in HarwellXPS as well. The issue with the DS line shape is it continues or extends to infinity, and therefore doesn't give you the best quantification possible. However, it is widely used in synchrotron data, so maybe worth you having a little look and playing around with those types of models and a different background indeed. We've used the Shirley. This, I believe, if I recall, uses a 2-guard or 3-parameter 2-guard type background. Okay, so going forward, that is probably the most difficult type of example that you will have there. What I want you to now do is, as I say, play around with making your own line shapes, see how they form, if they reflect on the data. It's perhaps valid if you can do a constrained model. Then move on to taking a model such as this and applying it to this oxidized carbon sample, and remembering the sort of parameters, the sort of regions where you would find a CO or COH bond, a carboxylate or carbonyl type functions in relation to a peak at 284.5 electron volts, based on the slides in the overview.